Space is a near-perfect vacuum. While it contains dust and gas, the particles are spaced so far apart that they cannot interact in the way required to transmit sound. Sound is a mechanical wave. It acts like a relay race where vibrations are passed from one particle to another through physical collisions. In our atmosphere, molecules are packed closely. A vibration strikes one, which hits the next, creating a chain reaction. In space, these particles are so distant that they rarely bump into one another. Because there is no medium to carry the energy, space remains silent. It is not the absence of energy, but the absence of a pathway for sound to travel. Sound is a mechanical wave, which travels as a physical chain reaction between particles. Think of it like a line of dominoes, where energy is passed from one molecule to the next. In our atmosphere, these vibrations create zones of compression and expansion. This anatomy of a longitudinal wave shows how density changes as energy propagates forward. Transmission depends entirely on density. In solids, particles are tightly packed, allowing for rapid energy transfer. In gases, like our atmosphere, particles are spaced out, yet still frequent enough to maintain the wave. Space is a near-perfect vacuum. Here, the mean free path between atoms is so vast that they cannot physically collide to pass on their vibration. Without this chain reaction, sound simply cannot exist. On Earth, our atmosphere is a dense medium. Molecules are packed tightly, allowing vibrations to pass easily from one to the next. Sound is a mechanical wave. It relies on a chain reaction of collisions between particles. Without enough particles, the wave simply cannot travel. While space is not truly empty, it is an ultra-high vacuum. In a nebula, gas particles are spread out over such vast distances that they cannot carry the energy required for sound to reach human ears. The silence of space is not a lack of energy, but a lack of proximity. The particles are physically too far apart to vibrate in unison. It is a common myth that space is nothing but an empty void. While it is true that human ears cannot hear in the vacuum of space, space itself is far from dead. Space is alive with plasma waves, gas pressure ripples, and magnetic vibrations. These are physically sound waves moving through the sparse material of the universe. So why do we perceive space as silent? These waves exist at extremely low frequencies, often tens of octaves below the limit of human biological perception. The silence of space is a limitation of our biology, not a total lack of physical energy. If we had the right sensors, space would be a very noisy place. Since space is a near-perfect vacuum, we cannot hear it directly. To explore the cosmos, scientists use a technique called sonification. This process involves converting non-auditory data, such as X-ray intensity or radio signals, into audible sound frequencies. By mapping these data points, we can translate complex stellar activity into patterns the human brain can recognize. This is not a recording of actual sound, but a powerful analytical tool for visualization. It is crucial to remember, sonification is an analytical tool for interpretation, not a literal recording of physical sound waves. It helps researchers detect patterns in data that might remain hidden in visual graphs alone. Deep within the Perseus galaxy cluster, a supermassive black hole sits at the center, surrounded by hot intergalactic gas. Astronomers detected giant pressure waves rippling through this gas. These ripples are literal sound waves, traveling through the medium of the cluster's hot plasma. These waves are massive, yet their frequency is roughly 57 octaves below middle C, far too low for human ears to perceive. To hear them, NASA scientists scaled these frequencies up by quadrillions. This process, known as sonification, converts physical data into audible sound. Human brains are remarkably efficient at processing rhythmic and frequency patterns. The primary auditory cortex allows us to perceive shifts in sound that visual charts often hide. Scientists deal with complex data. While powerful, visual identification of subtle, periodic shifts can be incredibly taxing and imprecise. Acoustic astronomy transforms raw data into audio. By mapping signal intensity to pitch and volume, we unlock a secondary data analysis channel that is highly attuned to change. This integration of sight and sound, known as multimodal analysis, allows researchers to listen for anomalies in the universe that visual analysis might simply overlook.